In this video, we'll be looking at something called the limiting reactant. So we won't always have an unlimited supply or equal quantities of reactants. We're going to run out of something first, and when we do, the reaction will be over. So looking at this little example I have here, I have my red reactant, my blue reactant, and then my multicolored product. So I have 10 of my red reactant, 6 of my blue reactant, and when they combine, they form this multicolored product. And in my product, I have 6 blue and 6 red. So if you notice, I have used up all of my blue reactant, but I haven't used up all of my red reactant. I actually have 4 pieces of my red reactant left over. So my red reactant is going to be in excess, meaning that I'm going to have some excess of that reactant left over. Okay, now let's look at one more familiar example. So let's say in my recipe or my reaction for making s'mores, I have 72 graham crackers, 4 marshmallows, and 150 pieces of chocolate. How many s'mores can I make? Well, I can only actually make 4 s'mores because I can only make as many s'mores as my least amount of ingredients. So if I only have 4 marshmallows, I can only make 4 s'mores. My graham crackers and my chocolate are going to be in excess. And my marshmallows are what we're going to call our limiting reactant. They're going to limit, this reactant is going to limit how much product I can make. The limiting reactant is the reactant that produces the least amount of product. It's the one that limits the reaction. In our example, our marshmallows were the limiting reactant. I could only produce as many s'mores as I had marshmallows. The excess reactant is in unlimited supply, or there will be some of this reactant left over after the reaction stops. In our example, our excess reactants were both my graham crackers and my chocolates. After I made my 4 s'mores as determined by my marshmallows, my limiting reactant, I was going to have some chocolate and graham crackers left over. So let's take a look at an example. Example number 1 asks, given the reaction below, if 5.7 moles of C4H10 reacts with 8.9 moles of O2, which would be the limiting reactant? So this is my balanced equation, which remember we're going to use like a recipe. So this tells me if I have 2 moles of C4H10 combined with 13 moles of O2, I'll get 8 moles of CO2 and 10 moles of H2O. But they're telling me rather than 2 moles of C4H10, I have 5.7 moles, and instead of 13 moles of O2, I have 8.9 moles. But I can still use these molar ratios to determine the quantities that I have for my reactants and products, given the amounts given. So to find my limiting reactant, I need to know which of my reactants is going to produce the least amount of product. So it doesn't matter which product I use, I can choose one of them, and I'm going to use stoichiometry to determine how much of one of these products each of my reactants are going to produce. So let's start with what we're given, and we'll start with our C4H10 since that's listed first. So I have 5.7 moles of C4H10. And I can choose either product to solve for, but since CO2 is first and it has a smaller number of moles, I'll use that one to solve for. So I'm going to solve for my number of moles of CO2. And so I set up my conversion factor, so my moles of CO2 over my moles of C4H10. And to get my numbers, I go back up to my equation and look at my mole ratios. So I have 2 moles of C4H10 and 8 moles of CO2. So my 8 moles of CO2 to my 2 moles of C4H10. So my moles of C4H10 are going to cancel. And I'm going to be left with 22.8 moles of CO2. So now I'm going to repeat the process, but with my moles of oxygen gas. So if I have 8.9 moles of oxygen gas, I want to know how much CO2 that will produce so I can compare it to the amount of moles produced by my C4H10. So I do my mole ratio step again, but this time with oxygen gas and CO2. So I go back up to my equation and I have 8 moles of CO2 produced by 13 moles of O2. And my moles of O2 are going to cancel, and I will get 5.5 moles of CO2. So from my 5.7 moles of C4H10, I produced 22.8 moles of CO2. And from my 8.9 moles of O2, I only produced 5.5 moles of CO2. So my oxygen is going to be my limiting reactant because it produced the least amount of product. With 8.9 moles of oxygen, I can only produce 5.5 moles of CO2. So as soon as I produce that 5.5 moles of CO2, I'm going to run out of oxygen. Whereas my 5.7 moles of C4H10 can produce up to 22.8 moles of CO2. So I can produce a lot more CO2, a lot more product from my C4H10 than I can from my O2. So to help you tackle these problems, here's a couple simple steps you can follow for your limiting reactant questions. Step number 1 is choose a product to solve for if there is more than one. Step 2, solve for the moles of the product or grams if asked using each reactant. So sometimes they may ask you the amount of grams of product produced, in which case solve all the way to grams. If they simply ask you what the limiting reactant is or to identify the limiting reactant, you can just stop once you've converted to moles of product. And number 3, step 3, the reactant that produces the least amount of product is the limiting reactant. The other reactant or reactants will be in excess. So let's take a look at another example that asks us something a little different. Example number 2 asks, how many liters of gas are produced when 28 grams of NaHCO3 reacts with 28 grams of HCl? So notice we actually have equal quantities of our reactants, but we can't just assume that if we have equal quantities of reactants, we're going to produce equal quantities of products. Because remember, these have different molar masses and are very different molecules, so they are going to produce different amounts of products. So we still have to go through and use stoichiometry to figure out which one is our limiting reactant. So we start with what we are given, and we'll start with NaHCO3 since it's first, and we have our 28 grams of NaHCO3. And since I have grams, using my stoichiometry map, I have to go from grams to moles. And I find that my molar mass of NaHCO3 is 84. So I now know how many moles of NaHCO4 I have, so that crosses off. My moles of NaHCO3 goes on the bottom. And now I'm at my mole ratio step. So I'm going to be solving for a mole of my product. And they were specific. They asked me how many liters of gas are produced. So they told me which product to solve for. The only gas I have in my products is my CO2. So I'm going to be solving for liters of CO2. And from my mole ratio step, I know that for every 1 mole of CO2 I produce, I'm going to use 1 mole of NaHCO3, and that's by looking at the coefficients from my reaction. So my moles now cancel, but I have to take it one more step since they specifically asked how many liters I'm going to produce. So my moles of CO2 goes on the bottom and my liters of CO2 goes on the top. And this is my molar volume of a gas. And I know that 1 mole of any gas is 22.4 liters. So that cancels and I'm now left with my liters of CO2. So I do my calculation and it comes out to 7.5 liters of CO2. And I just wrote it up here so that I could see that NaHCO3, when I have 28 grams of NaHCO3, I'm going to produce 7.5 liters of CO2. So now I have to figure out how much CO2 I'm going to produce from my 28 grams of HCl. So I'm going to set it up very much the same way with my molar mass of HCl here, my mole ratio step here. For every 1 mole of CO2 produced, I'm going to use 1 mole of HCl, and then finally my molar volume step here. And when I do my calculations, my 28 grams of HCl is going to produce 17.2 liters of CO2. So clearly I can see that my NaHCO3 is my limiting reactant because it only produced 7.5 liters of CO2 gas, whereas my my HCl could have produced 17.2 liters of CO2. So my HCl is going to be in excess and my NaHCO3 is going to be my limiting reactant. So finally, let's take a look at example number 3, which asks, if 18.1 grams of NH3 reacts with 90.4 grams of CuO, how many grams of excess reagent will be left over? Reagent is just another word for reactant. So reactant and reagent mean the same thing. So there's kind of a lot to unpack with this example. So they asked me to find grams of excess reagent. If I need to know how many grams of excess, I need to know which of my reactants is going to be in excess. And to know that, I need to know which of my reactants is going to be my limiting reactant. So this is, surprise, surprise, a limiting reactant question. So as with our steps, I noticed, as with the steps we saw earlier, I noticed that I have more than one product. So I can choose whatever product I want to determine my limiting reactant. And so since N2 has the simplest number of moles, it's only 1 mole of N2 in this reaction, I'm going to use N2 to solve for, but I could use copper or water, it doesn't matter. And since it asked me how many grams of excess, when I do my conversions, I'm going to go all the way to grams of N2 rather than just stopping at moles. If they just asked me to identify my limiting reactant, I could stop at moles. But since they asked me for grams of excess, I'm going to go all the way to grams. So here are all my steps. I started with what I was given, and then I used my molar mass to convert to moles of NH3. Then here is my mole ratio step so that I can go from moles of NH3 to moles of N2 using my mole ratios from my reaction, my 1 mole of N2 to my 2 moles of NH3, and then finally my molar mass of N2 to get the grams of N2 produced. So once I do my calculation and a little bit of rounding, I'm going to produce about 15 grams of N2 from 18.1 grams of NH3. So now I have to do the same thing for my 90.4 grams of CuO to determine which is my limiting reactant. So I start with my 90.4 grams of CuO, use my molar mass of CuO to get into my moles of CuO, my mole ratio step to go from moles of CuO to moles of N2, using the mole ratio from my reaction, and then finally my molar mass of N2 to get 10.1 grams of N2. So obviously my CuO is my limiting reactant because it only produces 10.1 grams of product, whereas my NH3 is going to produce 15 grams of product. But they didn't ask me which one was my limiting reactant. They asked me how many grams of excess reagent will be left over. So I'm actually really interested in my NH3 as my excess reagent. I want to know how many grams of NH3 I'm going to have left over at the end of this reaction. Once I've used up all of my CuO and my reaction stops because CuO is my limiting reactant, I know I'm going to have some NH3 left over. And what this is asking me is how much NH3 I'm going to have left over. So in order to do that, I actually have to work with the amount of product produced from my limiting reactant. So I am only going to produce 10.1 grams of N2 in this reaction given 90.4 grams of CuO. I can't produce any more because once I produce 10.1 grams of N2, I'm going to run out of CuO, my limiting reactant. So what I can do is I can work backwards. I can say, well, all right, if I have 10.1 grams of N2 produced, how much NH3 does that require? And I can work backwards to figure out how much NH3 I need to produce 10.1 grams of N2. So when I do my stoichiometry backwards, I find that if I start with 10.1 grams of N2, or if I produce 10.1 grams of N2, that is actually going to require 12.3 grams of NH3. So I use stoichiometry to go backwards. I started with my 10.1 grams of N2, use my molar mass of N2, my mole ratio to go from N2 to NH3, and then finally my molar mass of NH3 to figure out how many grams of NH3 is required to produce 10.1 grams of N2. So if I started with 18.1 grams of NH3 and I used 12.3 grams of NH3, all I have to do is a little subtraction, subtract what I used from what I started with to get my excess reactant left over. So after my reaction stops, I will actually have 5.8 grams of NH3 left unreacted. So here are some steps that summarize how to find the amount of excess reactant left over or left unreacted. So you're going to use stoichiometry to calculate the number of grams of excess reactant required to produce the least amount of product. So you're going to take whatever your least amount of product is that you calculated in finding your limiting reactant and go backwards to calculate how much of your excess reactant you're going to use to produce that amount. Then when you get your answer, you're going to subtract that from the original amount of excess reactant given. So whatever amount of excess reactant was used in producing your least amount of product, you're going to subtract that from your original amount of excess reactant, and that will tell you how much excess reactant you'll have left over once your reaction stops. If you would like a more advanced and much faster way of finding your limiting reactant, excess reactant, amount of excess reactant left over, watch video 4.2b that shows you a much faster shortcut, but it is a bit more advanced. So if you'd like to challenge yourselves, take a look at that video to find out a much faster method of doing this whole process. Otherwise, bring any questions you have with you to class.